So we move now to the other side of the world. We go to Australia with James Brandley, who is a CTO of Diffuse Energy and has a background of mechanical engineering and a PhD at the University of Newcastle, where he focused on materials storing thermal energy. And then after that, he co-founded Diffuse Energy, of which he will now tell us a little bit more. James, are you there?
Yep, I'm here. Can you hear me okay?
Yes.
All right, just give me...
Good evening.
Yeah, so it's a late afternoon here. So once again, thanks heaps for inviting me. It's great to be part of all of this. Sorry, I'm just trying to... So hopefully you can see my screen now properly. So yeah, we're, I guess, one on the other side of the world, and also probably a bit of a change of pace from small wind turbines to really small wind turbines. So we're on the really small wind turbine end of it.
Switch to presentation mode. We see also the next slide.
What's going on there?
There should be something like switch display.
Broken everything now. Why has it done that to me?
Display settings on the left should be. Yeah.
How's that?
Perfect. Thank you.
Okay. Yes. So today I'll give you a bit of introduction to our small wind turbine. Over the past couple of years, we've been running a project with the Australian Renewable Energy Agency, funded by them, which is kind of centered around the application of our turbines in remote telecommunications and sort of stretching into remote data applications, predominantly on farm. Then I'll talk a little bit about some complications of control of micro turbines, and further to Alessandro's great point just previously, some difficulty in predicting site power output, and then later about some supply chain difficulties, which we may not be alone in. So, as you said, myself and co-founder Joss Kesby came out of the University of Newcastle. Our core ability is the ability to design a diffuser augmented wind turbine quite well, I guess, and that was out of Joss's PhD. So there's a photo of our little turbine there. In the application of remote telecommunications, predominantly we're competing with the cost of diesel. So many sites in Australia, at least, run wholly on diesel or on diesel with a supplementation of solar, but typically there's a diesel generator running there once a day or more frequently. So the idea was to offset some or all of that diesel. The other great thing about telecommunications is we can mount directly onto existing infrastructure. And, you know, as we all know, wind is quite complementary with solar. Don't think I'm telling anybody anything new there. And we had remote monitoring, so we can see what the turbines are doing in real time. So a little bit more about our turbine. So most of the turbine is made here in Australia, with the only thing really is the generators. There's no one in Australia building generators, unfortunately. So it's only quite small, just under 1 metre in diameter, less than 20 kilos. Quite happy to survive in more than 150 kilometres an hour. We've measured that a couple of times out in the field. Rated output of 200 watts, peak of around 650, depending on some system parameters. And everything on the turbine is designed to last for 20 years. So the plastic has a 20-year UV protection, and obviously stainless steel for most of the components. There's some aluminium components, but they're a marine grade cast aluminium. So yeah, the project that we've undertaken over the past couple of years has been with ARENA. So ARENA's fantastic in kind of looking at new technologies in the Australian landscape. The project originally was meant to go a little bit shorter, but unfortunately COVID happened just after we started, and that kind of, you know, made life difficult for all of us, as we all know. Partner companies. So there's 3 partner companies that we installed sites with, predominantly on the East Coast, but a couple on the West Coast of Australia as well. Here's some of our installations, some on larger telecommunication systems and some on some quite small ones. For example, the one there down the bottom with the 2 turbines is in southern Australia, on a fairly peaky hill, and you can see for probably 20 kilometers in every direction, quite flat. So it's like a really good spot for small wind turbines. And then the top left-hand corner is on a more traditional telecommunications tower up on the escarpment on the east coast of Australia. We did install these on smaller telecommunication systems, so more point-to-point array rather than sort of the one-to-many 4 or 5G standard telephone towers, which use, you know, upwards of 10 or 15 kilowatts. So a typical installation for the kind of sites that we're using run on DC. And I guess the fun part is that you've got a solar panel and a solar controller, or a wind turbine and a wind controller, and a diesel generator and a diesel generator controller, all sitting on a common DC bus, which makes control of the whole system kind of interesting. And then on the output side, they'll have, you know, DC or AC systems running the communications. Predominantly in Australia, it's either 48 with some 24 volt DC and a very few 12 volt DC, but that's quite rare. So a big part of our, I guess, you know, we designed the turbine back in sort of 2016, 17, did a whole pile of wind tunnel testing and thought we're pretty clever because we'd made quite an efficient turbine. And then once we stumbled into the telecommunications market, realized that we needed to be able to get the electrons out and put them in their systems. And that's where the fun kind of started. So our controllers evolved over a couple of years. And I guess the biggest challenge for us is twofold. One, normally it's assumed that a micro wind turbine is going to have a person around in a storm. Our turbines are mounted out in the middle of nowhere. And so if it does blow 150 kilometers an hour, there's no one there to, you know, tether the turbine or shut it down. So we needed to be able to stop the turbine in those situations. Yeah, and so we actually short the windings on the generator, and that stops the turbine in much less than a second. And the other is for small turbines, the reaction time of the turbine is really, really quick. And so typical small wind controllers are kind of based off a solar controller, and the control loop on those just isn't quick enough to keep up with what happens. So our turbine controller can stop the turbine on a range of conditions, being, you know, over current or over voltage, or if the thing gets too hot, we can shut it down as well. That's a problem in Australia because, you know, it gets up to 45 degrees out in the middle of the outback. So appropriate control of small wind turbines is pretty important. This is from the early days. So this is 2 power curves. One of them, we basically had a calculation error in it when we were first doing some testing. But you can see these 2 power curves aren't a mile apart. One of them is the correct one, being the blue data there. The other one was incorrect, being the green data. These are 2 turbines that are mounted or co-located on a site. They're about 6 meters apart. And you can see here that there's a 37% power difference between those two turbine outputs just based on the control curve. Realistic, like they're orthogonal largely to the prevailing wind speed, so that they don't interact with each other too much. So it just shows the importance of having good control. So I didn't mention earlier, our control loop, operates at 5 kilohertz. This is just for the nerds out there, a piece of data. So our turbine will accelerate if let go from sort of 600 RPM to 1200 RPM in well less than half a second. All right, question? Sorry, that's okay. And then with our remote monitoring on numerous occasions, we've measured well more than 100% changes in power output in quarter-second intervals. And so to keep up with that control and, not have the turbine run away on you in gusty conditions is pretty important. The other thing we had was remote, so that we could look at our turbines and see what they're doing, was this remote monitoring. We also plugged Luft anemometers into these so we could measure wind speed. We can log these up to 20 hertz. Don't do that very often. It's usually only when something exciting is happening. The dashboard will display information at about 2-second intervals, but we can download the data at full speed. And that's allowed us to kind of see, what's going on in edge cases to help us refine our control algorithm. So the outcomes of this last couple of years of testing is we've seen that originally we were aiming this at the larger point-to-point antenna arrays, which sort of sit around 700 watts to 1.5 kilowatt continual load. Unless it's a really, really good site, our turbine's a little bit, single turbine's a bit undersized to have a good impact. Like, it has that impact, but it's not really a good enough impact. However, smaller systems like the on-farm systems there that sort of run down, 250 watts is probably a common load on those. The turbines do really well at complementing solar, and we've got quite a few sites now that the diesel generator or petrol generator is just there just in case, rather than operating all of the time. Something that we found is that very careful consideration of site selection is super important, and I'll show a bit more on that in a moment. But we've put some turbines in places where we've got it wrong, and the output from the turbine's just been terrible, to be honest. And so getting that right so that you don't annoy customers is pretty critical. And just for fun, high frequency, like logging 10 hertz data out in the field in the middle of nowhere, racks up an awful amount of data, but is also kind of problematic just to have a system out in the field that's doing that long term. And so it's not recommended for just normal use cases. It's okay for, if you want to get your science on, but not great for a long-term solution. So more about power prediction. So we use a number of, of wind prediction data sets. So one that was produced by the CSIRO, who's Australia's science body. There's a little image there on the left-hand side. You can zoom right into about 1 kilometre square. It'll give you average wind speeds over history. And then the other data set that we use is the NASA wind data set. Oftentimes they'll agree quite well, but occasionally, and here's an example here, you can see, one's predicting 1.2 kilowatt hours a day, the other one's predicting 0.2 kilowatt hours a day. And so when that happens, it's, you kind of start guessing. We've refined, there's a fair bit more that goes into our calculation here. This is just sort of the back end of it. And we've been refining that over the last couple of years, and we've gotten a lot better. But every now and then you do find a site where you have this huge disparity. It's not very confidence building for either us or the customer to go and install a site there. So yeah, and for micro wind turbines, it's not really feasible to go and do a long-term wind study normally, unless it's a very critical site that's got big problems. And then the final part is supply chain for our controller. So we spent a long time developing our controller, and it uses a lot of components that are fairly unique, so that they don't have comparative parts. And we've had components now that have been off market for, just about 18 months with no clear end in sight of an ability to get them. And furthermore, the parts that we can get, the bill of materials cost has nearly trebled. So we're kind of in a position now where we've got a potentially long wait ahead of us to get our controllers back on the market. So we've been, we ran out of controllers about 6 months ago. So we're kind of in a wait and hold situation at the moment, which is not the greatest place to be. So that was a fairly quick one. I wanted to leave some time for questions, if anyone's got any questions.
Yes, thank you very much.
There's no questions. I'll thank everybody for your time and allowing me to come and present.
Thank you for joining. Is there any question from the audience? Doesn't seem so. So then, as usual, you can just put them in the chat or write directly to James.